Going to dive right into function families and transformations. A function can be transformed by making small changes to the function that doesn't change its general type. For example, I wrote here linear or quadratic functions would be different types of functions. So we'll label the parent function as f of x. That's just a convention. And we label transformations of f of x as g of x. Again, that's just a choice going way back in algebra. A parent function and its transformation are considered to be a part of the same family of functions. So we just want to get used to the language here. Parent functions are the simpler functions f of x, and then when we change them, they'll be transformations, but they'll all be a part of the same family. Here's our first type of transformation. How about a vertical translation? These shift a function up or down by a constant amount. Now, we'll write that the transformation g of x for the general form of vertical translations is equal to, I'm going to write two things, f of x plus k for a shift up, or f of x minus k for a shift down. That's the general form. And by the way, for all of these, k is just a constant. Some constant, like a number, like 5. Okay, so let's take an example. Let's consider the parent function x squared. So our parent function is f of x is equal to x squared. Write g of x, its transformation, if f of x is shifted up by 2 units. Well, if we follow my rule up top, g of x is equal to x squared plus 2. Shift up by a constant amount, 2. Graph f of x and g of x and fill out the table. All right. I want to make a quick pointer. Today, I'm going to save time in the video and make it go smoother by not flip-flopping back and forth to different screens. You can see I've got Desmos up here, and I also have my calculator available. Let me graph this one up by hand, and then I'll just show you Desmos once quickly. F of x, if I input these values, which I'm sure you did in Algebra 1 to graph up a quadratic, negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So I'm going to graph up our familiar old quadratic here. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Notice this is hopefully a familiar quadratic. It's symmetric. Its vertex is right there at the origin. And it doesn't matter if you square negative 2 on the left side, it has the same symmetric value as squaring positive 2. Now, if you want with these functions, I'll do this in blue, we can just take all these values. I can take this 4 right here, and I can just shift it up by 2 values to 6. Shift 1 up by 2, 0 up by 2, 1 up by 2 again, and 4 up by 2 again. And this is a valid way to perform this function. You can see how I'm kind of getting these values quickly by hand, because these are small enough to do so. So I can graph these points, negative 2, 6, negative 1, 3, 0, 2, 1, 3, and 2, 6 up here. And you guys can see that this is indeed a function that is shifted up consistently by these 2 units right here every time. Okay? So that's easy enough to do by hand. How would I do it in a calculator? Well, hopefully from class yesterday, you guys are all confident enough to answer that question on your own. Here's what I have in Desmos. I just want to show up quickly. Desmos is nice. You can see here I have my parent function in red. I have my transformation in blue. And you guys can see, you can just quickly play with these functions on Desmos and see the shift up. If I wanted, I could also shift this down, right? And you can see that blue function shifts down. later when we have more complicated transformations. Here's something we'll be doing in a moment. I can shift this to the right by 2, which we'll see in a little bit, and you can see that blue function shifted all the way to the right. I know I haven't explained that yet, but just look what's happening visually. I just want to point out, you can pull up a Desmos tab, and you can use it to help answer these transformation functions by seeing what effects these tweaks have on this parent function, and you can do it in real time very quickly. You can see for the examples in the notes, I also have all these tables already laid out with all the values that I'm going to write in the tables. And hopefully from Desmos yesterday, you guys got a feeling about how to construct that. So if you weren't confident getting these values by hand, you could construct a table of values like we did yesterday to do so. I'm just not going to do that myself every time, so I'm not flipping back and forth between screens on this video. Very quickly, for our TI-84 friends here, I'll flash this up on the screen. Notice if I hit second table on this graph, I also have all of these table values laid out in the graphing calculator. All right, and these are coming from y equals. I just put the same functions here. You can see y2, I have that x squared plus 2. These are the values right here for y2, or for y1 rather. No, y2 here that I have in the notes. By the way, quick note for the calculator people, hit second y equals for stat plots to turn your plot off, and if you want to go back to a normal window for this, hit zoom and go down to zoom 6 for standard and hit enter to get back to your normal -10, +10, -10, +10 window, and you can see all the things on the graph. So let's keep going here, and I'll do all the rest by hand. Let's do horizontal translations. The general form of horizontal translations. To shift, I'll fix this on your copy. This is supposed to say left or right by a constant amount. Let's take the general form. G of x is equal to, and there's two cases. This one's a weird one. You want to take note of this. X minus k, if I subtract k from the inputs, actually has the effect of a shift right. You might normally think shift left there. Be very careful, so I'm going to star this. It's not intuitive. There's a mathematical reason for that, but I'm going to leave you guys. You can prove this to yourself right now if you try this on your graphing calculator or Desmos. And if we add a constant amount k, that will shift left by k. Left by a constant amount k. All right, so let's do example 2 just like we did before. Consider the parent function f of x is equal to x squared. Write g of x if f of x is shifted right by 2 units. So if f of x is x squared again, that's the parent function. In blue, I'll write g of x, our transformation, and I'll use a pair of parentheses and make sure that these shifts left and right, we're sliding along the x-axis, so we're only shifting our inputs. So I'm writing a -2 right next to my x value here, and then I'm squaring it outside of the parentheses, and that is a shift left by 2. This is the same old function we had up top, 4, 1, 0, 1, 4, and then for g of x, this is all shifted to the left. If you do plug this into a table of values, you'll find this, 16, 9, and then you'll see our pattern repeat, 4, 0, and if I continue down here to the values 3 and 4, this value will repeat right here. Basically taking the end of our normal quadratic here, that's normally way up above the axes that I gave you on these notes, right? It would sail way up above the left side here. That's what I have sitting over my value of -2, because I've taken that value up way into the left and I've dragged it over to the right. So I'm actually only going to graph these values here for this function because that's all I have room for, and you can see these inputs were all shifted down, right? My normal value from 1 was shifted down to 3 here to the right by 2 units, and this value for 2 was shifted to the right by 2 units. So if I do graph this up, it looks like my normal quadratic, but -1, 4, 0, sorry, by 2 units, that was a mistake. 0, 4, 1, 1, so this value overlaps, 2, 0, 3, 1, and 4, 4. And you can see for this transformation, this is indeed shifted over to the right by 2 units. Moving on. Stop and think. The video will pause. Is the transformation g of x is equal to x minus 2 a shift down or a shift to the right by 2 units of the parent function f of x is equal to x? And if you got this trick question, it's both. Both transformations are mathematically identical. That doesn't happen for all functions. It wouldn't happen for the quadratic. But this line here, f of x is equal to x, it's so simple, it's not complicated enough for there to be a difference between the shift down or the shift right. And you can prove that to yourself on Desmos. By the way, fun fact, the textbook is incorrect about that. It calls that a shift down. It really could be described by both. Reflections over the x-axis occur when the y values or outputs, let's think of these specifically as the outputs, are negated. That's how I encourage my students to conceptualize reflections over y. So the general form of this is very simple. G of x, the transformation for a reflection over the x-axis, the whole function f of x is negated. So we just stick a negative sign out front. I'm going to do reflections with the y-axis right along with this. This is when the x values or the inputs are flipped or negated. And maybe you can stop and visualize that now. Flipping over along the x-axis, or along the x values rather, will flip over the y-axis. And the general form of this, I know this looks very similar, but it's not. It's an important difference. You'll find just your input value, your x, however many times x occurs in your function, and you'll stick a negative sign right there inside the parentheses with x. This just negates your input values. Let's try both of these in one. Reflect the figure about the y-axis below. You can see I just have a segment with endpoints -1, 5 and -4, -1. First reflected about the y-axis, then reflected about the x-axis. So let me reflect it about the y first. I can take this point here and I can just visually flip it over the y-axis. But notice this is following my rule about the coordinates. I have labeled the coordinates of both reflections. This is where I just change the sign of my x value. So I go from -1 to +1, 5. The y value doesn't change. We can do the same thing over here. Change the sign of my x value. This will be at 4, -1 over here. +4, -1, and you can see this is a visual flip over the y-axis. In blue here, let me do then reflected about the x-axis. So I'll take these points now, so I'll start up here with 1, 5, and now I'll flip the y value. So 1, -5 down here. And I'll do the same thing. 4, -1 becomes 4, +1. And note that if this is below the axis, now it's going to flip up above the axis, and I can connect this. So we've now graphically translated this segment by 2 reflections across the y and then the x. Let's take a look quickly about how this works algebraically. So I've just got 2 quick examples. No, one example here, example 4. Let f of x be equal to the parent function 3x plus 2. And then let g of x be a reflection of f of x over the y-axis, and h of x be a reflection of f of x over the x-axis. Write the function rule for g of x and h of x. I asked, what are g of x and h of x? So let's do both of those. Let's take it just step by step, and I just want you to notice the difference between these two. G of x is a reflection of f over the y-axis. So reflection over y, g of x is equal to, well, I'm going to take f of x, 3, and I'm going to stick a negative sign in front of my x value. And that will simplify to -3x plus 2. So you can see that plus 2 doesn't change, and if you graph that up, you should be able to see that reflection across the y-axis. But algebraically, this looks a little bit different. What if I flip over the x-axis, and I said let h of x be the transformation of f over the x-axis? I have to stick a negative sign out in front of the whole function, which is why I'm using these parentheses here, and you can see I have to now distribute that negative, and this is different. Hopefully you can see that. Takes all the values and flips them and negates them. And this would be a line with now a negative y-intercept over here. And so that's the difference, at least on paper, for a reflection over y and a reflection over x. Here's one more stop and think. Would f of x equal to x squared plus 2 change at all when reflected over the y-axis, y or not? So the answer to this is no. No, it would not change, and I'll give a short mathematical reason. First of all, this is a quadratic shifted up by 2 units. If you can visualize that or stop and graph it up, this will not change if I flip it over the y-axis because it's symmetric. And that's also because if I do change the inputs with a negative sign, well, negative x squared plus 2 is equal to x squared plus 2. There's no mathematical, algebraic, or graphical difference. And I'm going to try to speed things along here because I can't let this video go on too long. These vertical compressions are not so bad, so I might go through this a little bit quickly. But if I vertically stretch or compress my function, this happens when f of x is multiplied by a factor. So a vertical stretch is going to be g of x is equal to a times f of x, a factor times your function, where specifically a is greater than 1. And a vertical compression occurs when you have the same thing. You multiply your function by a factor. Same thing, except that a is in between 0 and 1. So I call these big a's over here, although that's not really a mathematical term, and these are small a's over here. So let's look at this. We have example 5. Let f of x is equal to x squared, and then let g of x be equal to 1 over 4 times x squared. So is this a stretch or a compression? This is a compression, right? 1, 4 is indeed less than 1. It's like multiplying by a small factor. So this is a compression. And let's just see that in the graph real quick. This is the same function we started with up at the beginning. So I'm going to go ahead and graph this guy up. Here's our normal f of x, and I haven't been labeling these. I should have, but I have been color coding them. This, if we take all these values and multiply by 4, we'll get 1 and 0.25. 0 times 1/4 is still 0. 0.25, and then we'll get 1. And if I graph these up, you can see that this basically looks like this original purple function, and it's just squashed. Out here, the higher these values are, the bigger the difference, the more down they get squashed. And as you go towards the origin, you can see I'm drawing smaller arrows here towards the origin. The squash gets slower, so this is not exactly like a shift down, but all these values are kind of reduced by the same scale factor. 2 quick examples here. Let g of x be the graph of f of x is equal to 4x. Compress this vertically by a factor of 1/2 and then reflect it over the x-axis. What is g of x? Okay, so if f of x is equal to 4x, compressed vertically, let me do the compression first. G of x will be equal to 1/2 times 4x, which is equal to 2x. Then let me do a reflection over the x-axis. I take that 2x and I would say, well, over the x-axis, I just put a negative sign out in front, and that's equal to negative 2x. So our final answer is g of x is equal to negative 2x. And I just want to make one small note here. Mult by a factor of negative 2 is 2 transformations. As you can see here, it's both a stretch by 2 and it's a reflection with that negative value. So, describe the transformation of f of x given the following information. F of x is equal to 2x squared, and then g of x is equal to negative 6x squared. I'm going to lay this out quickly here at the end of this video. Hint, order matters. If you're ever confused about this, go left to right. And I want to show 2 things here. If f of x is equal to 2x, I'm just going to lay this out. 1, this is specifically first a reflection over x, then a stretch by 3 left to right, then a shift down by 1. And this works algebraically because if I take those in order, I'm not going to prove this to you on a graph right now. But this works because if I take this in order, I take my parent function 2x squared, I reflect over x first. I put a negative sign up front. Then I'll multiply by 3, and then I shift down by 1. And you guys can see that will wind up with negative 6x squared minus 1. Or the other way to do it, if you do change the order, you need to be mindful of this. I can do my stretch first. If you do change the order, you just have to be careful. I stretch by 3, then I can shift. But if I shift first, before I reflect, I have to shift up by 1. And then, finally, I can reflect over x. And I'm just going to leave you with this sort of algebraic proof. If I do that, so I take my function 2x squared. First, I multiply it by 3 for the stretch. Then I shift it up by 1. And then, if I reflect over x, I have to change all of the output values for the whole function to negative. And so you can see here I get that 6x squared, but I'd have to distribute that negative sign through. And I'll probably do this later in class, but you can prove yourself by doing this in order on a graph that these transformations in these specific orders are going to result in the same function. But I would encourage you can just stick with the first way and stick to my rule. With order mattering, with order of operations here, you can always just read it from left to right as you describe those functions.